Hello, everyone. I'm Boyu. I'm a PhD student from Loughborough University, and this is the topic today. And let's start. It's working. Okay, yeah. So this is part of my presentation today. So as we know, the 3D printing of composite or polymers are rapidly increasing these days, and however, the application in marine industry is not very well developed. This is one of the 3D printed PLA ship propellers made by the one shown below. Is the laser point working? Oh, okay, yeah, it's this way. Yeah. So the laser, as shown the literature below, yeah. So as we see that in 3D printed composites, there are defects like this shown here. So it's nature and cannot be changed. I mean, it could be reduced by changing the printing parameters, but yes, due to the printing manufacturing method, there will still be such a defect. So in the water diffusion of 3D printing, we have to consider such a defect as shown in the previous slide. But however, in previous researches, most researchers focus on the entire block and consider the printed polymers as a homogeneous material. So however, the capillaries do accelerate the water diffusion in the composite in the polymer very fast. So let's have a look. So this is the basic rule of the capillary force in 2D, and I'm going to use it in my later research. This is the constitutive model in the capillary effect, as we see that the capillary effect and the water pressure push the water into the capillary, and the air trapped inside the capillary, and the dynamic pressure and the viscosity forces, they are the force that retard the water flow into the capillary. And here is the function of the constitutive function from the literature shown here. And this is the fixed law, which is the diffusion of water in the matrix. So here's the material property from the literature shown here. So let's have a look at the effect of a capillary shape. This is my previous one of my previous research. It is a perfectly round capillary tube in a module which is 1 millimeter wide, 0.1 millimeter high, and 100 millimeter long, which is a typical situation in one printing bead. And there's a 0.03 millimeter capillary penetrate inside through the entire module. As we could see here, that the with the capillary, the time that the water reaches a saturation state is significantly accelerated. And here is the process and the result of from the result of abacus. And this is the forces distribution during the capillary during the flow in the capillary forces, as we could see through time, distance and time, as we could see that the purple line, which is the dynamic pressure, the orange line, which is the viscosity forces, they are very minor compared to the water pressure, capillary force, and the air pressure inside the capillary. So in my previous research, it's a perfectly round capillary. And as we know that in real situation, the capillary shape is irregular. And these are some, I made some other models, which is a diamond, a triangular, and this one model. We try to see that what does the shape of the capillary affect the shape, the speed of the capillary flow. And these are the forces distribution. As we could see, the capillary force, which are related to the perimeters of the capillary, is they have like that. And the water pressure and air pressure, they are related to the cross-section area of the capillary. So those are the distribution of the delta differences in the forces. So these are the total forces and total pressure, because the area are different. So we need to consider the different area in the forces. So the pressure is more significant. As we could see, the triangular one has the highest total pressure here. And this is the final capillary flow length. And the triangular one penetrates the most longest distance. So the conclusion is the capillary with smaller cross-section area, meanwhile, it has the longer parameters relatively, penetrates farther. And then, yes, and therefore the capillary with a more complex shape has a higher penetration distance because it has a relatively smaller cross-section area and larger parameters. So what about the void shape? Why I say void shape is when the water penetrates from the direction which is perpendicular to the void or the capillary. These are the 5 different shapes I'm going to discuss. And there are 2 types of void. Void type 1 is the pure hydrophobic one. The air inside the void doesn't take up any water. And then in the second type, it is a hydrophilic one. The air in the tube absorbs water, and the data are from the literature below. Yes, so we could see this first one is type 1. So in type 1, the void are hydrophobic and it retards the penetration of the water. And in the second one is hydrophilic. So as we could see that the purple line here, which has which CO15, which has the largest radius of the circle one. So it means that it's major dominantly affected by the cross-section area of the void inside. And in the figure C, it shows the void solubility sensitivity study. So as we could see that if we reduce the void solubility, it has minor influence here. But if we increase, the water have to fulfill the void itself. So the speed of diffusion is reduced. So here are the result from Abacus. As we could see that in the hydrophobic void, the big void shape here retards the penetration of the moisture significantly. And however, in this one, in void type 2, which is hydrophilic, such a big void accelerates the diffusion of water significantly. And this is the mass flow rate. As we could see, it's very interesting because in the second void type, there's a tunnel. There's a tunnel as we show here. The gray one is because it's above the maximum range of the lesion here. So there's a vertical channel, and there's a vertical tunnel. So water are going through the void and then penetrate and then diffuse into the matrix in that way, as we could see. Yeah, so the conclusion is if we consider the void, if it is a hydrophobic or hydrophilic, the hydrophilic void has a higher diffusivity compared to the matrix and act as a channel accelerate penetration of water. And future work, I will consider the capillary effect and the hydrophilic void inside it together, and then explore the shape of the void in 3D model, because previously I did in 2D, and I will combine it with a real specimen together as well. Yeah, that's it. Thank you.